request? We got 4, we got 7. Any others? 1? Can't do all of them. Seriously, let's put 4 and 7.
Was 7 the shadow?
Yep.
Yeah, it's the pool and the shadow. The swimming pool and the shadow is these 2. Okay. All right. We'll see if anybody comes up with any more as we go then. Okay, we'll start with the swimming pool, number 4. Okay, so let me pull it up. I remember all the details. Okay, a swimming pool is 50 meters long by 20 meters wide. Its depth decreases linearly along a length from 2 meters to 1 meter. So all right, so that's basically my swimming pool. I got 1 here, and then there's my 3, and this is 20 by 50, and our swimming pool. And it is initially empty and is filling at a rate of 1 cubic meter per minute. How fast is the water level rising 250 minutes after it filling begins? How long will it take to fill the pool? Okay, so we are pulling water into this, and my water level is at some point like this. All right, so that's my water. Okay, and I'm just going to, the water does continue on over here, but for simplicities of labeling and all that stuff, I'm only going to color in that one, those 2 dimensions, that one side. Okay, because I have wonderful options. Yeah, you wouldn't be able to read it if I tried to do it that way. All right, so this is what we're looking at, and so what's my variables? What's going on? What can I label on here? Okay. Of what? The pool? Well, the length and width of the pool is given, 50 and 20. The volume of water. So looking at the water. So the blue there that we're looking at. So I'm going to call this W for the height of the water. So W for water there. So I'm going to let W equal the height of the water. And what would be my units of measurement for that? Meters. So that's going to be in meters. And we can let L here equal the length of the water's height, the length of the water, to the top of the water, however you want to state that. How did I say it? The surface length of the water. That's good. And that unit is also in meters. We were given that it was initially empty and it is filling at a rate of 1 cubic meter per minute. So we know 1 cubic meter per minute. In calculus notation, what is that equal to?
The rate of volume.
So that is the rate in which the volume, we're filling up the tank, is changing over time. So that's the rate of that volume of the blue area, the water area, over time. All right, how fast is the water level rising? So what are we trying to find? How fast is the water level rising? So we're trying to figure out dW dt. And we're trying to figure out that when or after. Well, I guess I did. After 250 minutes. So when T is equal to 250.
So dV over dt represents the change in volume.
The change in volume. And the volume, because we're pouring it in at that rate, that's the rate at which the volume is changing.
Known volume represents the height.
No, not necessarily.
So what's dV?
That is the rate in which this, because here, you know, that length, that L is short, it gets longer and longer and longer. So the rate in which that's getting longer,
Oh,
the surface area, surface leak, not area, surface leak, the water. Which is, but dW, so that's the dW is the rate in which the water is. So how fast it's filling up, that's rising, the water level is rising. Okay, so, whew. I know, so this is what you want to get to in every related rate problem. You want to get to a rate you know and a rate you're trying to find. That's why it's called related rates. We're relating two rates together. So that means when I do that, I'm going to look at the variables here. So that means I need to write an equation that relates V with W. So that's my next goal, is to find an equation that I can have V is equal to something in terms of W, or other way around. So V equals what? So W is dealing with the water. So how can I figure out the volume of the water at any given instant? Don't know, don't use any numbers yet. Any of those like 12 or those given numbers. We don't know numbers yet.
L W times the width times the angle at the bottom.
Well, what kind of, this is our next question.
Oh, this
We have to figure out,
triangle.
did I draw it correctly? It is the water level down here where it is a triangle prism, or did I draw it wrong? And is the water level now above that line where it's going to be a trapezoidal prism? Is there any way I can figure out, should I draw on the line as I did here, or should I draw it above the green line? So we need to calculate the volume at the green line to figure out where it switches from that triangular prism to the trapezoidal prism. So I change it to shape. So I got to do a little work before I can get to this. So I'm not quite ready for that yet. So we're going to find the volume of the bottom part of the swimming pool. And that's represented here by where that green is cutting off. Okay, so green and below. So we need to figure out where it breaks up. So when you're finding the volume of a prism, or any type of prism, you find the area of the base times it by its height. In this terms, the area of the base is this triangle right here. That's going to be called my area of my base. That's the common shape that's going to happen throughout. So what, and that's going to give, so how do you find the area of that green triangle? 1/2. For the green triangle, what is my base height? Nope. 2. Because the total is 3 minus that 1 meter that we're cutting it off at. Okay, times by the height, 50. Times by, so that gives me the area of the base. Now I need to times it by the width of this. So how many of those? 20. All right. So that gives me 50 times 20.
Yes.
1,000 cubic meters. So in order to hit the green line, I had to have pumped in at least 1,000 cubic meters. If I did over 1,000 cubic meters, my water is already above that. If I did less than it, my water is below it. How can I figure out what I did?
You had the time. So
So we know we're pumping it in at 1 cubic meter per second. And the water level that I'm focusing on is after 250 minutes. So I only have 250 cubic meters in there. So I know I drew it right. The water level is below that line, which makes it easier for us because we don't have to worry about the trapezoid right now. We can just do the triangle shape of that. But you do have to figure out which one it is, where it falls. Questions over that? I see some question looks. Huh? Yeah, but we don't need it right now. We might need it for B, but we don't need it right now. All right, so back to the water. So to find the volume, now first remember how to find the volume of a trapezoidal prism. How would I find the volume of the blue? 1/2. Whoops, that's not a half. 1/2. What is my width? What is my base? W. What is my height? L. And what is my depth here?
whatever 20 you represent as, or you.
It's still the 20. That doesn't change. That's a constant in this. It doesn't change as we're going in the water. Water's going to spread throughout the entire base constantly. So we don't have to worry about that. It's changing. All right. So V is equal to 10 WL. Uh-oh, got a problem. No,
We don't know what W is.
we have too many variables. Exactly. We need to relate V and W. So I only need an equation with V and W. So I need to figure out how to write L in terms of W.
Pythagorean.
That's not a 3069.
No, it's not. We don't know if it is or it is not.
Does it have to do with Pythagorean?
Nope.
Okay. Sine.
I'll give you a hint. I have drawn a green triangle and I've drawn a blue triangle.
Oh, yes.
Similar triangles. If I look at those two triangles that I have on here,
They look pretty similar.
these two here, so looking at these two triangles, they both have right angles and they share this side, so AA similarity. So I can use similar triangles in those two. Okay, so I got similar triangles. So looking at the blue triangle, we have, go over here, so the blue triangle, we have its, yeah, funky move, you, okay? So here on the blue triangle, we have its width is to its length. As on the green triangle, what was the width again? W? 2. And what was the 40? So we can set that relationship. And then it's cross multiplying, we get 50 W is equal to 2L. Now, what variable do I want?
We want W.
We want W. So therefore, in this equation, I should solve for
W.
L.
Oh, yes, because, yeah.
Because I want to replace L in terms of W. So I want to solve for L. So that gives me 25W. So now I can go back over here and replace that L with 25W. So volume is equal to 250 W squared. Now double checking my work, I was given derivative of V and I want to find derivative of W. So I want an equation relating V with W. I got an equation relating V with W. So now I'm ready for the next step, which is derivative. Differentiate to get the rate of change. What's the derivative on the left-hand side? dV dt. And what's the derivative of the right-hand side? 500 W times by dW dt. Don't forget the implicit. All right, now plug in what we know. Well, we were given that dV dt is 1, so I can replace that with 1. I wanted to find dW dt, so that's my variable. But I do know, well, I gotta get rid of that W there. So I gotta figure out
Maybe we could solve it for W right there.
how can I find W?
Would we not use the similar triangles?
No, because we don't know L either, so that wouldn't help us.
We know the volume at 250 minutes.
Oh, we do. What is the volume at 250 minutes?
250.
So volume at 250 minutes equals 250 cubic meters. How'd you get that? Because the volume that it's filling is 1 cubic meter per second. Per minute, sorry. So we know that that volume is that. Okay, how does that help me?
We can take V is equal to 250 W squared and replace V.
So the instant we're looking at, we can replace that V with 250. And we can solve for W now. So we can use that volume formula that we had for the water. And the water level is that the instant we're caring about is at the 250 minute instant. And so that just gives us 1. And so V is equal to plus or minus 1, but in this situation, W is the height of the water, so which one of those makes sense? Positive. Can't have a negative. So that means that my W here is only 1 in this case. So I put in a 1 there at this instant in time. So dW dt is equal 1 over 500. Now I need to take care of my units. What was our W being measured in? Meters. And what is T time being measured in?
Seconds.
Not seconds. I think it's minutes, right?
Oh, it is.
Minutes.
Yeah, minutes. Okay. And the water level is hot and rising, so it makes sense that I get a positive. So that's how you get 1 over 500 meters per minute.
Is a question like this gonna be on the test?
Yes, that can show up. Absolutely.
Yay.
Are we having 3?
We'll talk about that after we talk about this. I'm doing that right after we finish reviewing over the worksheet. Don't let me forget, so remind me. Okay. Question part B of this. How long will it take to fill the pool?
So
So we're trying to figure out how long to fill the pool.
we need to find the volume of the pump.
Oh, so we already figured out up here, we found the volume of the bottom. So let me write that down, sorry that. So volume of bottom, we got as 1,000 cubic meters. So we need to figure out the volume of the top. Okay, so how would I find the volume of the top? Okay, so 50 times 1, that gives me that distance times by 20. Okay, so 50 times 1 times by 20, which is equal to,
1,000.
that's also 1,000. So the total volume would be that 1,000 plus that 1,000. So that is 2,000. Keep writing cubic with a C there. Cubic meters. So how long will it take?
2,000 minutes.
Therefore, it takes us 2,000 minutes to fill the pool. So your sentence would be something like, it would take 2,000 minutes to fill the pool, or you could actually convert that to hours and minutes if you wanted to,
Years.
but you can keep it as 2,000 minutes. Everybody okay now with number 4?
You make the tough part look so easy. I spent like an hour on it. Or
Once you see it, it becomes easier. Yeah, but you have to kind of see, and these same tricks come up over and over again. All right, number 7. What was our next one? All right, number 7 was the person walking, right? Moving shadow. Okay, so for number 7, we have this person. So we have this street light that is 20 feet high. Okay, you have a street light that's 20 feet high. And you have this person that is, and you always assume the ground is level, at least they say otherwise. So we have this ground that they're walking on, and this person that is 5 feet tall is right here. And so we're looking at this distance here.
That's a pretty skinny person.
Okay, I know, my artistic work is great, isn't it? And then we have, so the street light, the light is coming in this direction. This is the shadow that's forming from that person. So that's that person's shadow right down there. Okay, and so if that's that person's shadow, I'm gonna call that S for the shadow. Okay, so I'm gonna let S equal the length of the shadow in feet. Okay, so that's going to be my length of the shadow in feet. Something else that's dynamic and changing is that person is walking closer and closer to the street light. So this distance here is also changing. So I'm going to call that D for the distance she is from the street light. And my units will be feet as well. Okay. So I got that going on so far. What else was given to us? The woman walks at 8 feet per second toward the street light. So we got 8 feet per second. What would be our calculus notation for that? dd. dd dt, derivative of d with respect to time, would be that 8 feet per second, for 8 feet per second. And then we want to find out what is the rate of change of the length of the shadow. So we're looking for the S dt. And when do we want to find that? We want to find that when she is 15 meters from the street light. So that means when D equals 15. Okay.
Is it okay to assume that because the ground is oval, that the pole is straight up?
Yes. Yes. Yes, you always make that assumption too. So there's going to be a right angle there. Okay, and so I need to relate D with S. So I need some equation that relates D and S together. Ideas. So she is using similar triangles. So she's taking this triangle here, and she is relating it to the beat triangle here. Again, they both have right angles. We assume the person's standing straight. and they share that angle. So we got angle similarity. So I can use proportions. All right, so to set this up, we have this length of the purple triangle is to the height of the purple triangle. Okay, what's the length of the blue triangle?
15 plus
S plus D. Do not substitute in the 15 until after differentiating, because this is when the derivative equals that. So you cannot substitute in until after you differentiate. That's the key. That's one of the very common errors that's made. So you want to make sure that you get that straight. So we cannot ever substitute that occurring when it's special case occurring until after we differentiate. Over 20 is the height that we're looking at. Okay. So again, cross multiplying. So I got 20s is equal to 5s plus 5d. So that's 15s is equal to 5d. And I'm looking for ds, so I can go ahead and solve this equation for s. So s is equal to d over 3. I'm going to write that as 1/3 d, just because sometimes that's easier for people to see the differentiation than that. Okay. So everybody, now what do I do? Differentiate, find our derivative. Because now we're ready. We have it in terms of this variable d and s. And so now that I got an equation in terms of those two variables, the one I know and the one I need to find derivative, I need to find the derivative. So what's the derivative over the left-hand side? That is just ds dt. And what's the derivative of the right-hand side?
DD.
1/3 dd dt. Okay, plug in information I know. I know dd dt is 8. Technically, it is actually -8 because she's moving closer, and so that distance is decreasing as she gets closer to it. So I'm going to actually plug in a -8. Okay, so ds dt. So it's -8/3. Okay, what is s's unit of measurement in? Which stands for the length of the shadow? That's feet. And what is time in measured in? Seconds. So the shadow is shortening at a rate of 8/3 feet per second. If we had sentence that you can form from that. Second question. At what rate is the tip of the shadow moving? So I'm going to go back up to my equation here. And I'm going to add in another variable here. And I'm going to let this distance here represents the length of the tip, big T for tip. Okay, so now I got big T is equal to the distance, the tip of the shadow, is from the light, the straight line. And that's being measured in feet. Okay. So I know, actually I know ds now, so I know s, I know d, I know ds, I know dt, dd. And so I want to figure out the rate of change of that tip. So that means I want to figure out d big T over d little t is what I'm trying to figure out. So I need to relate big T to, say, S or D, one of those variables.
D plus 1/3 D. T plus D plus 1/3
Well, how'd you get that?
D plus S. Whereas is 130 D.
Okay. So T is equal to S plus D. Okay, and then what? I got too many variables. I mean, I could do it. I guess we could. Let's try it. I haven't done it like this yet. Okay, well, yeah, we can change it, but we also have all the derivatives of that if we wanted to. Let's try it and see. How would I differentiate the left-hand side? That's dt over dt equals
S, D, S, D, T.
ds over dt. I'm curious to see if this method works. And equals plus
D, D,
dd dt. Okay. Oops. We know that dd dt is the -8.
Oh, it's positive. D, S, D, T is negative.
Oh, I did the wrong one, right? ds dt is negative 8/3. And dd dt is -8. So let's we get a common denominator. So I need to multiply this by 3, right? Okay. What's -8 minus 24?
32.
-32 over 3. So big T is measuring in what units? Feet, and time is being measured in
Per second.
seconds. And so the tip of the shadow is decreasing at a rate of 32 over 3 feet per second.
So what I did was I established a ratio between the two triangles. I said the larger triangle is always going to be 4 times as big as the smaller one. So I just multiplied, I just said therefore dt over dt is equal to 4 ds dt. And that got me the right answer. Would that be like correct work?
How did you get to it's always 4 times? Because of this ratio here, 5 times 4 equals 20?
Yeah.
And so you know that S times 4 has to equal the D, or the big T, sorry, big T.
Yeah.
Absolutely. That'll work as well. That absolutely works. That's another approach to seeing it. You just saw the ratio of that. Any other problems? Scroll down. Any other questions that you want to work? Number 1? Okay.
Oh, that was whenever I was like 1, 2, 3.
That should be okay.
You want 1? Yeah. Okay. So 1. All right. Starting on, let's see. It was given that the sides of a square increase at a length at a rate of 2 meters per second. So sides of a square. So we have a square. I'll call sides S. Okay. So let S equal the length of the side of the square. And we are in meters. Okay, we know that the side of a square, sides of the square increase in length at a rate of 2 meters per second. So this 2 meters per second is equal to what calculus notation?
Velocity.
Okay, ds dt. Okay. Now, in part A is asking us at what rate is the area of the square changing when the side is 10 meters long? So we want to find what? dA dt when S is what? 10 meters. Okay, so when S is 10 meters. So that means I need an equation that relates A and S. Okay, area of a square equals side squared. So A is equal to S side squared. Notice you didn't have to identify the S here. Notice I didn't identify the A because we're using the traditional symbols for the area of a circle. So if you use the traditional symbols in a formula, you don't actually have to write the definition, but if you use any other variables, you do. Or if you have multiple lengths and widths and heights and stuff like that, that's when you need to start doing it. So it's okay that I didn't define the A. So I've already got it fixed. So now it's just differentiating. So what's the derivative of left-hand side? dA dt. What's the derivative of the right-hand side?
2s dt.
And then plug in what we know. We were given that S is 10 and ds dt is 2. So that gives us 4 times 10, which is 40. What is the unit measurement for area? Meters squared. And what's the unit measurement for time? Seconds. So the rate in which the area is changing is 40 meters per second squared. Meters squared per second. So that backwards. Meters squared per second.
Meter squared per second and meter per second squared are the same thing.
No, technically, depending on where your parentheses are, on what you're reading it, it could be the M and the S are squared, or just the S is squared. So what I said was just squaring time, not squaring meters.
Okay.
So meters squared per second. All right, B, at what rate is the area of the square changing when the side is 20 meters?
That might just be double.
It's the same thing, just plugging in.
Just 2 times
So
20.
this time we want to find dA dt when S is, what was it, 20?
Yes.
Okay, so for B, we're just doing it when it's 20. So I go back to my derivative equation, dA dt is equal to 2s ds dt. And this time I'm replacing s with 20. My rate for ds is constant. And so this time I get 80 meters squared per second. Okay, and then B, look at my derivative equation. The derivative equation is 2s. Okay, so it's a linear relationship. And so for C on the graphing of it, we have this one point here at 10 seconds. We're up to a height of, so we want, this one is measuring seconds. This is area, not seconds, sorry. What did they ask us to do? Draw a graph of how the rate of change of area varies with side length. So this is my side length, which was S. That's where I got S from, which is my side length. And this is my rate of change of area. So that's dA dt. So when my side length was 10, I got at 40. When my side length was 20, I was up to 80. So we're looking at that wet path. And so of course that's going to continue in that pattern. You could try another point if you wanted to. So that's all you needed for the graph. And the main was labeling it. Okay. All right, so this is a review over, that was our worksheet, our related rates worksheet. After talking to a few people, I think that we need some extra practice on this. I'm not quite ready to move on to those topics on the video, so I'm postponing that. Today, we're going to do more practice with related rates. So you're going to have related rates worksheet number 2 to work on. And then you might want to refresh your memory on the mean value theorem and linear approximation before Thursday's class. And we'll talk about that on Thursday. But that means we don't have that extra period after Thursday's class, before our Monday test, to go over linear approximation mean value. And that's one of the things I promised that you would have. So your test will only cover implicit differentiation, and related rates. So we're going to change the test to only cover those two topics. And we'll move linear approximation and mean value theorem to the next exam. Okay, so that's what we're going to do, huh? Which would be after, yeah, after fall break. So on Canvas, you will find related rates worksheet number 2 that you can start working on. I have recorded the example problems today. And